Hello everyone, welcome again in Eng-Man YouTube channel. So in this video, we will continue our quick knowledge playlist. And today's topic is very important. It's very interesting. It's about virtual no-flow boundary. Okay, so here we go. All right, we start with this picture. It's a picture of a reservoir. And you can see this reservoir has some boundaries. And actually, they are not physical boundaries. They are not real boundaries like fault. They are actually virtual no-flow boundaries. So let me change my pen. They are virtual no-flow boundaries. They are just virtual. They are not real, but they exist and they have influence on the production, on the performance of this reservoir, on the drainage area. All right, so if you have a reservoir and if you have reservoir with multiple wells and they already produce fluid or gas or yeah, they already in production for quite some time, you will find or the performance will exhibit the existence of virtual no-flow boundaries. All right, so the key here is this one. The wells have been producing at constant rate or more or less constant rate for some considerable time. All right. So it's the key, it's the practical key, but in theoretical term, this reservoir has reached semi-steady state condition or pseudo steady state condition. All right. And you can see, we can read it together. So once the reservoir is producing under semi-steady state or pseudo-steady state flow condition, each well will drain from within its own no-flow boundary, quite independently of the other wells. So each well will establish their own drainage area. All right, that's very important. Virtual no-flow boundary. And virtual no-flow boundaries will change following the rate changes. So if the rate in some wells changes, of course, the no-flow boundaries will change as well. So when flow rate changes, drainage area will start to migrate, will start to reshape, and eventually reach a new configuration. All right, following the production, the current production of each well. Okay, so this is the example. All right. Further, okay, for this condition, dPdt must be constant throughout the entire reservoir. All right, that's the definition of semi-steady state condition, right? So dPdt must be constant throughout the entire reservoir. Otherwise, flow will occur across the boundaries, causing a readjustment in their positions until stability is eventually achieved. All right, so dPdt must be constant. If not, there will be flow from area to another area until eventually stability or equilibrium has been achieved. Okay? And the average reservoir pressure can be estimated using these equations. So let me cross that. Average reservoir pressure. All right, so you sum up the pressure multiplied by the volume or the flow rate of each well divided by the total volume or total flow rate. All right. And under pseudo steady state conditions, the reservoir pore volume drained by a well is proportional to that well's production rate. Okay. It's like this. So the pore volume drained by each well is proportional to the well's flow rate or production rate. If the well produces with low flow rate, small flow rate, then the drainage area or drainage volume will be small as well, and vice versa. And in the assignment of drainage area, any physical flow boundaries must be recognized before virtual boundaries are set. So it's like this. So if you know for sure that here you have fault, all right, it can be ceiling fault or it can also be leaky fault. You must set the fault first, and then you can consider about estimating the virtual boundary shape. Okay, so read the message here. Real no-flow boundaries such as ceiling faults must be respected before assigning virtual drainage areas or virtual no-flow boundaries. Okay, because it's physical boundary, real boundary. It should be prioritized. It should be respected before you set any virtual no-flow boundary. All right, so yeah, that's our quick learning. Again, it's a very important to help our understanding of reservoir characteristics, reservoir production performance, and pressure transient analysis. All right, so that's all. Thank you so much for watching. I hope you enjoyed the video. I hope this video is useful. See you again in the next quick knowledge episode. Thank you.